Hello everyone, my name is Angtian. Today I'm going to present our work, NeMo Neural Mesh Model of Contrastive Feature for Robot 3D Pose Estimation. So currently, render and compare-based object pose estimation approaches demonstrate lots of advantage compared to the previous T-point-based approaches. So benefit from the usage of dense representation, render and compare-based methods provide higher robustness. However, current render and compare-based methods conduct on pixel intensity level, which make these kind of methods have the following limitations. So the first one is the reconstruction loss of this kind of method is hard to optimize. And this method also needs instance-specific CAD models, which is expensive to collect. So to overcome this weakness, we propose NeMo, an object pose estimation method via feature-level render and compare. Also, NeMo only requires a simple mesh model for each category, which is easy to collect. So let's talk about how to train NeMo. We firstly uniformly sample vertices from the original mesh provided by the dataset. And we use the pose annotation to project each vertex onto the image manifold. Secondly, we use the CN backbone to extract the features from the training image. Then we use the feature map and the project vertex prediction. We can learn a per vertex feature representation. We call it neural mesh model. So next, we can calculate a reconstruction loss, use the feature map, vertex prediction, and the neural mesh model. Finally, just repeat step 2 to step 4 until converge. So during the inference, we first use the trained CN backbone to extract the features from the testing image. Second, we use the neural mesh model get from the training stage to render a feature map under a specific camera pose. And the camera pose is randomly initialized, and we are going to optimize it later. Third, we can calculate object score use these two feature maps. Similarly, we can also calculate a background score, use the clutter feature get from the training stage. And then we can calculate a reconstruction loss and the gradient update the camera pose. Finally, just repeat step 2 to step 5 like 300 times. Okay, so in the testing image, the occlusion is superimposed onto the object. And the second sub-figure shows how we optimize the object pose iteratively. And in the third figure, we demonstrate the real-time occlusion prediction. And the final figure shows the loss landscape and how current pose prediction is regarding the ground truth. Note that compared to pixel intensity level reconstruction loss, ours is much more easier to optimize as it's very smooth and have only one global minimum. So we conduct experiment on Pascal 3D Plus and occluded Pascal 3D Plus datasets. So the occluded Pascal 3D Plus dataset have 3 occlusion levels, with increasing occlusion from level 1 to level 3. Note that in the for the no occlusion case, NeMo already have higher performance compared to the baseline method under accuracy threshold pi by 18. So while with the increasing occlusion level, NeMo demonstrates much higher robustness compared to the baseline approaches. We also conduct experiments for pose estimation under instant views. Specifically, we split Pascal 3D Plus dataset into 2 subsets, front rear viewed subset and side viewed subset. And then we train on the front viewed subset and test on both separately. We can see that NeMo gave significant higher accuracy under the unseen views. So our code is publicly available, and thank you.